So the question that Buggy has is, what do you do when people are singing you happy birthday? It is a very uncomfortable thing, isn't it? Like, everyone's looking at you and you're just like, what do I do? So you just smile, I guess, and yeah, you like, you look happy, and then, yeah, you can't sing along, right? 'Cause, it's like, you know, when people are at the Oscars or whatever, and everyone's like clapping for, I don't know, whoever, Uma Thurman, I don't know what Uma Thurman was, like the first like name that came into my head, and like she's just sitting there like, you know, it's an awkward thing, right, when you're the center of attention. But okay, so let's go. Classifying chemical reactions. So our next couple chapters, chemical reactions, thermochemistry, and then we're going to go into stoichiometry for a couple chapters. So how to make sense of the infinite number of possibilities. So things you should know: chemical versus physical change. This is something that they hammer home starting in like middle school, right? You start talking about what's a chemical change, what's a physical change. So we're going to delve in a little bit, hopefully a little bit deeper than middle school. The types of interactions can tell you what is being changed. So during chemical reactions, bonds, either ionic or covalent, are broken and or formed. And during physical changes, intermolecular interactions may change, but the bonds remain intact. So we're going to look at... So the question is, and it's a great question, does that mean cutting a diamond is a chemical reaction? I have no idea what that would be considered, because that network covalent is a whole different thing. You are technically breaking covalent bonds. You're going to see we'll get to ambiguous changes. We'll put that in as an ambiguous change. Okay, so particulate view. So remember, chemical change is... Somebody shout a color. Purple was first. All right. So we're looking at bonds broken and or made here. That's a little too light of a purple. Yeah. Yeah. Okay. So I'm told never to use yellow or white as colors. Okay. So, all right, let's do this. We're going to look at a type of reaction that is a chemical change. And we're going to come back to this reaction later. So a chemical change, remember, just from the last slide, is bonds broken and or made. So we can show this using particles, our particulate representation. Now, I'm going to show it to you in two different ways. All right. The first way is I have my Lewis dot for methane. This is methane. This is natural gas. This is the stuff that comes out of your Bunsen burners. Yeah, like you guys all have Bunsen burners at home. Could be used to heat your house. Okay. So this is the Lewis dot. And then on the other side, we have this. So in this case, we can actually label the bonds that are broken, because all of these are broken. And the bonds that are made. Right, so by drawing the Lewis dots, we can see exactly what's happening. Now you might also see some people like drawing it this way with like this. You'll on the I think it was the practice test. was it that had like the molecule one that was like a long chain of just like circles as the particulate representation? Could look something like this. They look like eyeballs. All right. And then on the other side, you'd have the C here. O. O. And then O. H. O. H. O. H. H. So from both of these representations, you can see the bonds being broken and the bonds being made. I think the Lewis dot is better. We're going to hammer home Lewis dots a little bit more this year. I think most of you did really, really well on the Lewis dots on the test. I mean, there were only 3. So I was pleased with how that came out. All right. Anybody need me to wait a little longer? All right. So physical change from a particulate point of view. Remember, we're only, all right, color, green. This is only IM forces disrupted. So we have something, like, oh, not plus. Like phase change is a good example of a physical change. So here we have liquid, so we have and it's not, I'm not going to draw them as rigid. I'll just put like, they don't necessarily have to be hydrogen bonded together. You'll have some that are. And then this was a multiple choice question on your test, something similar to this. What happens when I move from a liquid to a gas with water? Spread out, be more specific. Individual molecules move further apart. And make sure you have the same number on each side. So that's what's happening during vaporization. That was another question. What happens during vaporization? The intermolecular attractions are completely overtaken. Yeah. Okay, so the question was, are they really completely, so we are assuming that they're completely gone, right? But you are correct that if you watch chapter 9 with the gases, right, we talk about non-ideal gases having some attraction to one another. They certainly would if they bounced together. They'd have some level of attraction together. But in general, we assume that it's gone. And then we could do it like this down here. Oh, that's an ugly one. All right, you know what? You guys, I don't want to draw that. It's ugly. You know what? I should. I'm going to use the growth mindset and tell myself I can do this if I keep practicing at it. All right. All right. All right. So essentially, these two things are saying the same thing. Thank you. All right. Okay. All right. So, but we also have some ambiguous changes. Oh wait, do we need to go back for a second? All right. That'd be gross. All right, are we good? All right. So, so like Eli said, ambiguous change. I have no idea what cutting a diamond would be, but there's a more prominent ambiguous change, and that is this. All right. So here, I have, oh, that's not correctly sized. So at the beginning, really? So there's a comment that, so maybe you can ask your boss. I didn't know there was a such thing as jump cutting school. I guess that makes sense, right? What's that? That's cool. All right. So then we'll have another 2 plus down here, another 2 plus over here. I don't want to keep going, but I need to have the right ratio. 2, 4, 6. Okay. Now if I put this into water, I'm going to make them smaller on the other side. I'm not destroying matter. I'm just going to make them a little smaller on this side because they didn't really fit. Two, 3. All right. So what do you guys think? Is this a chemical change or is this a physical change? It is an ambiguous change. Thank you, Eugene. Yes, it is. So you can argue that this is a chemical change because you're breaking ionic bonds. But you can argue it's a physical change because you're not really changing what you have. You still have, you can also write this as that. So when they first redid the AP Chemistry curriculum, Mr. Hamill and I were both happy because this is something, the idea of having solid lines between physical and chemical change is a little disingenuous because there are these ambiguous cases, right, that don't fit in perfectly to our definition of chemical change and physical change. But we can make some broad generalizations. So how would we identify? I don't feel like I got enough green. So I'm going to go back to the green. All right. So your big hint is to look at the chemical equation and or particulate representation. Right? Because from there you can see if bonds were broken or bonds. Look for bonds broken, made. So we can't, oftentimes, we never can see bonds being broken or bonds being made, right? We can't look on the atomic level. So we do need some sort of way of figuring out this just visually. What are some ways we can identify a chemical change just by looking at a reaction? So, yeah, explosion. We're just going to say heat released. This is generally true. Not always, because some physical changes can have heat released or absorbed. But an explosion is definitely, yeah, what you would probably consider a chemical change. What else are some? Yep. So properties changing. But that would be intrinsic properties, things like density, melting point, boiling point. What else could we physically see? Cooking. Right, so cooking, I think on the problem set there might be some around this, like, or maybe, I don't remember if we put that on, but like baking, why is baking bread a chemical change, but something else, but blending isn't? Making salad dressing is not, right? Okay, there are some other things. Cooking I'm going to put in the heat way. What visually can we sometimes see in chemical reactions? Yeah, there could be a color change. Oops. Yeah, that I would do, I was actually thinking I'd do each one a different color, but that would take forever. Color change. All right. There's one more that I would expect, one or two more that I would expect you guys to know. Okay, we'll put light up here. That is a good one. That's actually one I wouldn't expect you to know. Precipitation. Yeah, I hate that precipitation is what they use for rain. I mean, it's true. But like in this class, we think of precipitation as two solutions coming together and a solid being formed. What's another one that goes along like a different phase that you might see during a chemical reaction? Bubbles, gas. Now, people also say that physical changes are easily reversed and chemical changes are difficult to reverse. I don't know that that is a good definition of the difference between the two. We're going to do some equilibrium labs later in the year where we're going to have chemical reactions that we're just going to flip back and forth quickly, right? So chemical change, you're looking for, well, explosion, maybe. Hopefully not in this classroom. Changing properties, precipitation, gas release, color change. Yeah. Okay. So, why do we classify the reactions? Because we're looking for patterns. There are so many different types of chemical reactions, or so many different billions, infinite number of chemical reactions, near infinite number of chemical reactions, that if we just understand a few basic patterns, we can classify them and make it easier for us to understand. So we won't have to memorize each type of reaction. We'll just know a few different groups, and most reactions will fall under those groups for us to understand. So I also think, I'm going to take a step back. I also think pattern recognition is a really important skill for you guys to have. Like looking at nature, looking for patterns, trying to make some understanding from it. Unfortunately, humans are really good at this in general, probably too good at it. We look for patterns where there aren't any. If you take, how many of you guys are taking stats? Right, so you'll learn about you'll learn a little bit about that. But like when you are 21, if you go to a casino, or 18 in Canada, I think it's 18 in Canada. 19, sorry, 19. Yeah, I've actually been to a casino or two in Canada. But if you're playing, do you guys know what roulette is? It's the one with black. Eugene says he plays Russian roulette, which is not a good game to play. But if they show you all the past numbers that have come up, so you can see like, oh, if it came up red 6 times in a row, that means the next time has to be black. And it's not true at all. It's just equal odds. Like, it's the same as it always was. So humans are actually really good at looking for patterns because we've done that throughout our evolutionary history, and it's helped us survive. But too good because we look for patterns where there aren't any. But in this class, I want you to look for patterns where there are some. All right. So, classification of reactions. We are going to look at these main types. We're going to go through each one. Synthesis, decomposition, gross, combustion, precipitation, acid-base neutralization, and oxidation reduction. These we're going to examine in depth later in the year. I'm going to introduce both of them now, but the last month and a half of the year will just be these two things and solubility. I think we have 3 chapters on acids and bases. So I don't even say memorize, if you can recognize these types, you'll be able to make some predictions about what will happen when 2 substances are mixed. Okay. So, synthesis. In synthesis reactions, 2 reactants combine to form a single product. We call this marriage. A and B are coming together. They find each other attractive. They get together. So, an example of this would be all right. So in this case, I really didn't do a good job with this one. So, because there's so many, I'm going to have to sit down for this. So I have 8 irons. This is my diagram, or my particle representation. I have 8 irons, 1, 2, 3, 4, 5, 6, 7, 8. So I have iron here, and then I have sulfur. I'm going to make that yellow. Oh, you don't like, how bad is the yellow? It's real bad. All right. Well, because sulfur is yellow, but all right, we'll do S8. 1, 2, 3, 4, 5, 6, 7, 8. I don't think that's exactly how sulfur is bonded together, but let's just pretend it is for this. Okay. So, what changes between here, your reactant side, and your product side? What type of bonding is this? Metallic. And what is this? Shout that word that you guys just said. Say it again. Covalent. So I have metallic for iron, covalent for sulfur. And then what do I have as a product? Ionic. So see, I did all 3 types of bonding here. So when I show this, 1, 2, 3, 4, 5, 6, 7, 8. Whoops. Yeah, those are 2 minuses. All right. Oh, I should have picked an easier one, guys. I'm sorry. That's a lot. Okay, so in synthesis, we have marriage. In this case, we had a little bit of bonds being broken and bonds being made. It doesn't always have to be that way. But we have a new substance. Two become one. Do you guys know the Spice Girls? Is that they sing that song? And to become one. What's that? Oh, wow. I heard Scary Spice is my favorite. I heard Posh Spice is my favorite. Okay. So this is synthesis. Now, we're going to get to the sad one. Decomposition. This is divorce. I'm actually either going to make, I'm even going to make it in black. This is like when the attraction between them is no longer enough to keep them together. Their potential energy is too high. They need to move on, get to lower potential energy with other substances. All right. So Louis C.K. does this great. I shouldn't be talking about Louis C.K., but he was a Newton North graduate. So he talks about divorce, and when you say I got divorced, people are like, oh, I'm so sorry. No, you shouldn't be doing that, because if you got divorced and you're done with the divorce, that means your marriage was bad, and so you're happier when you're apart and back by yourself. So divorce isn't always a bad thing. Sometimes it's best for all involved. Okay. Okay, so this is an example of a decomposition reaction. This is hydrogen peroxide, which, when heated, becomes water and oxygen. All right. So this would look like hydrogen peroxide is one of those rare cases where oxygen is bonded to itself. I think some of you on your tests had oxygen bonded to itself. That's probably not such a good thing. So we have OOH. And then we get so we can see that we had a pure substance. Now we do not have pure substance. We have a mixture of two things. The next two are my two favorite. Okay. Am I cool to move on? All right. So, combustion, fire. Oh, is anybody in the Boy Scouts? I was in the Boy Scouts. I know Cameron is, but Cameron's not here. What's that? He might be doing Boy Scout things. I think Boy Scouts was most fun because you just got to make fires a lot. It was kind of fun. It was kind of fun. So, combustion reaction. Combustion reaction, a fuel reacts with oxygen. If the fuel contains carbon and hydrogen, then the products will be carbon dioxide and water. This is what we had on a previous slide. So I don't need to do the particle representation for this. All right. What I expect you to know. Yeah. The question was, are we getting all of lecture time? It goes fast. It goes fast. Right. Right. Yep. Okay. If you have a hydrocarbon or a sugar that you burn, right, your products are going to be carbon dioxide and water. Think about cellular respiration. Cellular respiration is essentially, we don't think about cellular respiration, is essentially a combustion reaction. You're burning a fuel, you're burning glucose, right, and you're getting carbon dioxide and water as a product. So your body is doing combustion reactions all the time. You just don't. When we think combustion, we think fire, right? I was what? Fire, fire, fire. What's that? I know, because it's cool, but it's a little bit of a misnomer, right? This is what we think about. We think about fire, but cellular respiration's one. Another example of combustion that we tend to not think about as combustion is this. Magnesium. If we burn magnesium, we get MgO. It is a cool. Yeah, I think it's like it's really, really bright. In fact, if we finish a couple minutes early, I'll just go get some magnesium ribbon and burn it, just because it's fun. Yeah. All right. I'll do. Yeah, I'm so blown away that you guys listen to it at 2x. I think that's awesome. Oh, do I talk fast? Oh. All right. I will work at slowing down. What's that? Yeah. Okay. So you can watch it. All right. So precipitation. This one's really interesting. All right. So in precipitation reactions, this is one that's going to come up a lot. A lot of your problem sets this. Two solutions of ionic compounds are mixed, and an insoluble ionic substance is formed. So here's the way you're going to see it written traditionally. And these are AQ, AQ. And then you get AD, AD, and CB. And one is solid. Now, this one, I go on a little rant about this one. So we had marriage and divorce. What would this be? Wife swap. So that is the way. That is wow. That's going to be really loud for whoever is like watching this because I just screamed that out. They're going to be at like, oh my god, I'm feeling terrible because they could be at home watching it and their parents are in the other room and all of a sudden out of nowhere they hear wife swap and like, oh, I'm going to lose my job. All right. Well, see, that's why this is my rant. Avery predicted my rant. I hate that it's called wife swap. Why is it not husband swap or why is it not just partner swap? It's very sexist that it was called wife swap. It should just why does it have to be that way? Why is it the woman who had to move in that stupid show? Okay. So Bucky just opened a can of worms. All right. So all right. I'm going to call this partner swap because I like to be open. I like to remove gender roles wherever possible. It could be for women, could be for men, doesn't have to be. All right. that totally made my day, Owen. Okay, so here is the particulate diagram. All right. All right. So you swap partners. The sodium, is the sodium going to go with the barium or the chloride? Chloride, how do we know? Because it's like salt. That is true. Metal goes with non-metal. So, and then BaSO4. We're not going to worry about balancing equations quite yet, but you need to know that there's going to go to there. So, one of these things is going to be solid, or else it wouldn't be a precipitation reaction. We would just say no reaction. So, which one, talk at your tables, which one do you think is going to be the solid? Okay, raise your hand if you think it's NaCl. Raise your hand if you think it's BaSO4. What if you don't have it? I didn't see all the hands. All right. So you should have known this from your background knowledge because water is soluble. Water is soluble. Salt is soluble in water, right? So what we're learning now is not all ionic compounds are soluble in water. Many are, but some are not. So what will this look like? Well, let's draw it. Lots of drawing in this lecture. These are beakers. These are my lovely beakers. All right. So you need to make sure your ratios are good. All right. So I'm going to draw and then Cl minus. All right. All right. One of the things, guys, that when you draw these representative particle diagrams, or the particulate diagrams, is you need to make sure you have the right ratio of stuff. So here I have 2 BAs and 4 CLs because I have BaCl2. So here I'm going to make, oh wow, 2, 3, 4, Na plus, Na plus, Na plus, Na plus, SO4 2 minus, SO4 2 minus. All right. For the next one, I'm going to make, I should have done it. I should have thought ahead. I didn't think ahead. All right, so I need a key here. Because I'm not going to be able to fit all this stuff in. So give me shapes. Just shout out shapes. Square, triangle, circle. Now I'm going to do the Superman shield. Okay, that's what I picked. I'm going to... It's a regular pentagon. All right, it's still a pentagon, but it's not a... All right. So, what am I going to put at the bottom? Together. All right, so I need to have the same number. So I'm going to draw square, triangle, square, triangle. Right? Because that's a solid, so they're bonded together, and the solid's going to sink to the bottom. How many circles do I need to draw? Talk at your tables. How many circles do I need to draw? In order to keep the conservation of mass constant. All right. Throw your fingers up in the air. How many? All right. That's 4 circles, because I had 4 circles over here. I had 4 sodiums over there, so I need 4 sodiums at the end, and then 4 Superman shields. You don't need to draw them as Superman. You can draw them as whatever you want. If you wanted to do the Star of David, that's totally cool. So historically I have been doing the Batman symbol in the past, but it takes a little while. I can do a really good Batman symbol though. Lots of practice. Oh, and see, now I'm under pressure. It's a little off center. Whatever. It's a little off center. Okay. My son used to ask me to draw them all the time. Okay, so this is the particular representation of a precipitation reaction. I would recommend, it's been a year, so I haven't thought about it. I would recommend you use the shapes. Make a key so you don't have to keep writing the letters and the charges in each one. This is a circle right here. Circle, 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 circle. Shield, 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 shield. Square, square, triangle, triangle. Which one? This one? All right. All right. So, oops. Okay, predicting. We're going to go down to the slide where we predict precipitation reactions, and then we're done for today. So, predicting precipitation reactions. Look at possible products by swapping the ions in solution. So since the reactants are solutions, all the ions are separated. Did I spell separated right? I can never spell. All right. I always stress out about separated. Just what? I got it. All right. So, and then if a precipitate forms, and these are based on solubility rules, a reaction happens. This is a terrible sentence because this. All right. If a precipitate forms, then a reaction does happen. No precipitate. And I'm going to, because chemists are lazy, we shorten precipitate to PPT, to PowerPoint. No precipitate equals no reaction. So you can mix two solutions and get no reaction. Like if I mixed salt water with calcium chloride, mix them together, no reaction occurs. But if a precipitate forms, then you do have a reaction. Oh, I spelled that terribly, huh? Is that? That's like participate and. Yeah, no, I knew how to spell it. I just was. Sometimes I go too fast. That's a word that I don't struggle with, but I just forgot. Okay. Now, I always try to tell you, we try to take as much memorization as possible out of this course. Here is one of those exceptions. Now, the no came out from the crowd. So, now, I'm going to tell you which ones to worry about. All right. This one is important. Salts containing group 1, the alkali metals, are always soluble. Na, always soluble. Li, always soluble. Potassium, always soluble. So salts containing group 1 metals or ammonium are almost always soluble. We're just going to say always for now. This is group 1. So look on the periodic table, group 1. All right. Salts containing nitrate, star, chlorate, we almost never talk about. Nitrate's the big one. Nitrate's the most important one. Nitrates are always soluble. Now, this is important because this is the anion that's most commonly used to solubilize difficult things to solubilize. Things that are typically insoluble, like aluminum, iron, things like that. We put them with nitrate and they'll dissolve. Gold. You can actually make gold nitrate solution, right? So it might actually be a problem on your problem set having to do, or at least when we get to stoichiometry, like how much gold can you get out of a solution of like 0.1 molar gold nitrate with, so what? Not alchemy, because we're not trying to change anything. Okay. Salts containing chloride, bromide, or iodide are usually soluble. This is a... Guys, and yes, I'm going to ask you to memorize some of these, but being honest, once you do a handful of these, you'll pick up some patterns, right? Because most of the time, it'll be something reacting with a sodium compound. So you know that that sodium compound, whatever it makes, is going to be soluble. One of the most popular ones is silver chloride. Silver chloride's insoluble. You mix sodium nitrate and, or sorry, silver nitrate and sodium chloride, and you get a solid. All right. Now we get into the ones that are less important to know, but still good to know. Sulfate are usually soluble, except with a lot of stuff, right? Carbonate, phosphate, hydroxide, usually insoluble. This one is probably more important than the others. And maybe carbonate too. There are a lot of carbonates out there. Okay, most salts are not covered by the guidelines. You cannot predict whether they are soluble or not, so you would look them up. At the end of the year, we haven't decided what our end of the year project is going to be yet. My first 2 years here, we did a 12 solutions lab, and that was a lot of figuring out like solubility of things. And that was actually really fun. We had to predict or you had to tell me what the identity of 12 unknown solutions was, just by doing tests. Yeah, Natalie. If they're not in 1 through 5, the 1 through 5, you look them up. Generally, they're going to be, though. And especially the ones we're going to use the most are the ones that I highlighted. All right. So last slide for today. Precipitation reactions. At your tables, predict what will be the product when we mix these things together. So talk to your peers. Try it. All right. So guys, I've written most of the stuff up on the board. Beware of charges. You have to check your charges. All right. So I balanced the first one. Guys, listen up. Shh. So I have sodium sulfate plus 2 silver nitrate makes silver sulfate. Remember, the charge of silver is +1. How do we know the charge of silver is +1? Because we know NO3 is -1. So if NO3 is -1, silver has to be +1. So what one, if any, is my precipitate? Silver sulfate. This is like the double whammy of solubility. Sodium and nitrate is definitely going to be soluble. All right, so I have lead acetate and aluminum bromide. Which one, if any of these, is going to be solid? Will be my precipitate. What do you think, Eric? Yep. And then this is a solution. Now we got to balance. What do I do? 3, 2, 3, 2. And then the last one. What do you guys think about the last one? Whoa, I don't know what that was. I heard like a yawn through a yawn. What do we think about the last one? Sodium iodide and calcium nitrate are my potential products. No reaction. Dun dun dun. They're both soluble. Number one trumps all. Sodium is going to be soluble. And NO3 is also always soluble. Yeah, Davis. So the first, like rule one, almost always soluble. Assume that it's going to be always. We would tell you specifically if it were not, right? But sodium, it's going to be soluble. Lithium soluble, potassium soluble. All right. Okay. So